Welcome to Homework Lib.
Here we're going to have NO2, which is a nonlinear triatomic molecule. And what we know is that in terms of the heat capacity of Cv, we can say that each degree of freedom is going to contribute to 1/2 on R per degree of freedom. We know that we're going to have 3 translational degrees of freedom. In this case, since the molecule is not going to be symmetric, we're going to consider the 3 rotational degrees of freedom. And we're going to have 3n minus 6 vibrational degrees of freedom. In this case, n is equal to 3 because we have 3 atoms, so 3 times 3, 9, minus 6, 3 vibrational. So the heat capacity is going to be quite similar to that of water and corresponds to a total of 9 degrees of freedom. So we're going to have, it would be 9/2 of R. And from the relationship that Cp is equal to Cv plus R, the value for Cp would be equal to 11/2 of R. So the values that we get when we replace the value for R, let me plug in here below Cv just to have it all together. 9/2 of R are 8.9415 calories per mole Kelvin. And over here, we would have the value for Cp, one value of R higher because we're considering that this is going to be an ideal gas and we can employ this approximation. Remember that this relationship in between Cp and Cp is only valid for ideal gases. So over here, the value becomes 10.9285 calories per mole Kelvin. So this would be our final results for Cp and for Cv. If you want to compare this, for example, with some reference, you can use the value of the heat capacity of NO2 coming from the NIST web page. So you're going to look up NIST webbook heat capacity or Cp for NO2, and you're going to find a very nice table. The values are going to be in kilojoules per mole, and just for reference, this value corresponds to 47.725 joules per mole Kelvin. So you are able to compare if this approximation is good or not for this particular molecule. Spoiler alert, it is going to be quite good. For example, the Cp at 600 Kelvin is 45.82. So it gets quite close.